Welcome to this cinematic biological explainer. Today, we're taking a microscopic journey deep inside the human bloodstream. I want you to picture an ultra-high-definition, Pixar-quality 3D animation zooming right past your skin, weaving through your blood vessels, and getting right down to the very molecules that keep you alive. We're diving into one of the most brilliant, elegant systems in human physiology, the oxygen dissociation curve. Now, I know that might sound a bit complex at first, but by the end of our time together, you'll see it for what it truly is, a beautiful, life-saving molecular dance. So, let's just jump right into it with a question. How exactly does a single, microscopic molecule inside your blood know the difference between, say, you sitting calmly on the couch with a cup of coffee and you sprinting at absolutely full speed on a treadmill? Your body doesn't just randomly dump oxygen everywhere, right? It delivers it precisely where and when it's needed most. This flawless, real-time logistics system is exactly what we're about to decode.
Here's our roadmap for today. 1. Hemoglobin as an oxygen carrier. 2. The math of oxygen in blood. 3. The oxygen dissociation curve. 4. Rest versus exercise. 5. The right shift of the curve. And 6. The Bohr Effect and P50.
Section 1. Hemoglobin, oxygen carrier.
Think of hemoglobin as the ultimate molecular vehicle. It's essentially a microscopic courier van designed specifically to transport oxygen from the loading docks of your lungs directly to the hungry tissues all throughout your body. And in biology, molecules really don't like to be single. They want to bind. Every single hemoglobin vehicle has exactly 4 seats, or 4 hands, if you will, ready to grab onto oxygen. It can't hold 5, it can't hold 6. 4 is the absolute maximum capacity for this particular molecular transport. If we look under the hood of this Ultra HD structure, we see that hemoglobin consists of 2 alpha chains and 2 beta chains. But the real magic? That happens right at the core, where we find iron ions in the Fe+2 or ferrous state. These 4 iron centers are the specific hands that physically grab the oxygen, and when all 4 hands are holding on to an oxygen molecule, well, the vehicle is completely full. In biological terms, we call this 100% saturation. At that exact moment, the hemoglobin's purpose is momentarily complete. It is fully loaded and ready for delivery.
Section 2. Math of oxygen in blood.
To truly appreciate how this system works, we kind of need to step into the biochemistry lab for a second and calculate exactly how much oxygen this molecular fleet can actually carry. Step 1. Research shows that 1 gram of hemoglobin can carry 1.34 milliliters of oxygen. Step 2. In a normal, healthy person, there are on average 15 grams of hemoglobin in every 100 milliliters of blood. So, if we just multiply that 15 grams by 1.34, we arrive at our golden number in step 3. Exactly 20 milliliters of life-saving oxygen is packed into every 100 milliliters of fully saturated blood. Lock that 20 milliliter number in your head for sure, because it is our fully loaded cargo baseline.
Section 3. Oxygen dissociation curve.
Okay, now that we know our cargo capacity, we're ready to look at the actual map this vehicle follows. This beautifully elegant sigmoid or S-shaped biological roadmap brilliantly illustrates the relationship between the environment and our molecular vehicle. On the x-axis, we have the partial pressure of oxygen, which is basically just how much oxygen is floating around in the surrounding area. And on the y-axis, we have the percentage saturation of hemoglobin. As the pressure of oxygen rises, like it naturally does in your lungs, the hemoglobin rapidly grabs onto the oxygen, creating this beautiful S-shaped climb. It hits its peak right in the lungs, where the pressure is high, reaching almost 100% saturation.
Section 4. Rest versus exercise.
But remember, the lungs are just the loading dock. What actually happens when the blood travels down to your tissues? Let's contrast 2 scenarios. First, calmly resting, and second, intensely exercising. Under normal resting conditions, your tissue oxygen pressure is around 40 millimeters of mercury. At this pressure, hemoglobin stays about 75% saturated. Remember our 20 milliliter maximum? If it stays 75% full, it holds on to 15 milliliters, which means it delivers just 5 milliliters of oxygen to the resting tissue. It's a pretty modest drop-off. But look at strenuous exercise. You're on a treadmill, your tissues are absolutely starving for oxygen, and the local pressure drops significantly. At this lower pressure, hemoglobin saturation plummets to 25%. It only holds on to 5 milliliters now, aggressively delivering a massive 15 milliliters of oxygen directly to your screaming muscles. It perfectly dynamically scales its delivery, based purely on what the tissue immediately needs. No waste at all.
Section 5. Right shift of curve. This brings us to a really fascinating biological phenomenon known as the right shift of the curve. Think of shifting to the right side of the graph as a dramatic breakup. It's the necessary dissociation or separation between hemoglobin and oxygen so it can feed those starving tissues. So what causes this molecular breakup? Well, imagine the fiery, high metabolism environment of a working muscle. It's using up oxygen, so PO2 is low. It's producing waste, so carbon dioxide is high. Lactic acid is building up, which means high hydrogen ions and lower pH. The muscle is literally heating up, so the temperature is high. All of these extreme working conditions actively bend our S-curve to the right. They act as biochemical signals screaming at the hemoglobin vehicle to drop the cargo right now.
And there's one specific trigger in there that requires a slightly closer look: BPG. Bisphosphoglycerate is a sneaky little molecule that ramps up during high metabolism. Remember those beta chains we talked about at the beginning? Well, here's a great memory trick for you: B for BPG and B for beta chains. BPG specifically binds to the beta chains of hemoglobin, and when it does this, it physically changes the shape of the hemoglobin, literally evicting the oxygen molecules and forcing that breakup right when the tissues need the oxygen the absolute most.
Section 6. Bohr Effect and P50.
As we enter our final section, we're looking at two biochemical definitions that flawlessly govern this entire delivery system. These are the ultimate takeaways, especially if you're a medical student or biology enthusiast. First up is the Bohr Effect. Discovered by Christian Bohr, this rule formally defines exactly what we've been observing. It states that an accumulation of carbon dioxide and hydrogen ions, meaning a lower, more acidic pH, directly forces hemoglobin to surrender its oxygen. When your muscles work really hard, they spew out CO2 and acid. The Bohr effect perfectly explains how this metabolic exhaust acts as the exact chemical trigger that unlocks the doors of the hemoglobin van, ensuring the oxygen cargo is dumped precisely onto the active tissues.
And finally, we have the P50 value. Think of this as the biological checkpoint for our molecular vehicle. P50 is simply defined as the specific partial pressure of oxygen in the environment at which hemoglobin is exactly 50% saturated. It tells us the exact moment the gas tank is half empty or half full, depending on how you look at it.
Normally, this 50% saturation checkpoint happens at an oxygen pressure of around 25 to 30 millimeters of mercury. But here is the absolute genius part of the system. When the curve shifts to the right during exercise, the P50 value actually increases. That means it takes a higher pressure of oxygen just to keep hemoglobin half full, which is just a fancy biological way of saying hemoglobin loses its grip and drops the oxygen off to you much easier when you're working out. So we've gone from the macro all the way down to the micro, from the air filling your lungs to the 4 iron hands of hemoglobin, right down into the fiery, acidic environment of a working muscle. Next time you push yourself in a really hard workout and you start to feel that burn, I want you to visualize this cinematic reality happening in slow motion inside you. Billions upon billions of hemoglobin molecules dynamically shifting their chemical curves, breaking up with oxygen at exactly the right millisecond, just to keep you moving, breathing, and alive. It is an absolute masterpiece of biological engineering. Thanks so much for joining me on this explainer, and keep marveling at the science inside you.